You read the title, it's as simple as that really. The outline for this proof is going to be as follows. We're going to prove the Pythagorean theorem as a consequence of the identity sine squared x plus cosine squared x equals 1. We will do this by defining cosine and sine in terms of multiples of the complex exponential e to the ix and e to the negative ix. We will prove these definitions using the Taylor series of sine x, cosine x, and e to the x. In order to find the Taylor series of some function, we must know its derivatives, which we will derive using nothing related to or derived from the Pythagorean theorem. First of all, we need to define a derivative to even find it. This is our roadmap. Let's see where it leads us and what difficulties we encounter along the way. First, the definition of a derivative. The slope, or the tangent line at a point, the rate of change, the instantaneous rate of change, or the derivative of f of x, written as f prime of x, is defined as the change in f of x over the change in x, with a motivation and geometrical interpretation as follows. The slope, or derivative, wants to measure how steep a line is. This is a very intuitive idea, hopefully, as for example, if you're walking up a mountain, the steeper the incline is, the harder it feels to walk up the mountain. For every step you take to the right, if you go up, then the function has a positive slope. If you don't go up or down at all, but stay on a straight horizontal, then it has a slope of 0. And if you move downwards, then it has a negative slope. Since for every step to the right, you move some negative vertical distance. Let's define this idea in the language of math. If our change in x is dx, then our change in f is f of x plus dx minus f of x. For a general function, this only gives you an approximation depending on how large dx, the change in x, or the step you take, is. However, if we take the limit as dx goes to 0, we get the paradoxical rate of change at a single point. Don't think about it too hard, okay? Therefore, f prime of x is the derivative of f of x defined as the limit as dx goes to 0 of f of x plus dx minus f of x, all over dx. Nice. None of this required the Pythagorean theorem or anything, so let's just get on with it. Also, in most textbooks, or generally anywhere you see this definition, instead of dx usually the letter h is used, but the meaning is identical. We now need to find the derivatives for sine of x, cosine of x, and e to the x. First of all, let's try this with an easier function to get a feel for how this will work, by finding the derivative of the simple parabola x squared. Therefore, f of x is x squared, so f prime of x is this. Expand this bracket. Then these two x squareds cancel, and we factor out a dx to cancel with the dx in the denominator. So then the limit as dx goes to 0 of 2x plus dx is just 2x. So the derivative of x squared is 2x. Now let us try to find the derivative of sine of x by plugging it into the definition for a derivative. We get this expression, but until now we also assume no knowledge of trig functions or identities, so we don't know how to simplify this. Let us derive a formula for sine of a plus b without Pythag. The definition for sine in a right angled triangle of an angle theta is the opposite side divided by the hypotenuse. For cosine, it's adjacent over hypotenuse. Make this sort of slanted right angled triangle with a hypotenuse of length 1 and an angle beta. Then the opposite side is sine beta and the adjacent side is cosine beta. Below this triangle, draw another triangle with angle alpha and base along the horizontal. Since it has a hypotenuse of cosine beta, the opposite side is sine alpha cosine beta, while the adjacent side is cosine alpha cosine beta. Next, draw a vertical down from the tip of the first triangle and a horizontal from that line to the tip of the second triangle. Because these two lines are parallel, this angle is equal to alpha. Furthermore, this angle plus alpha equals 90 degrees, so it's 90 degrees minus alpha, so this angle is alpha in the triangle with a hypotenuse of sine beta. The adjacent side is thus cosine alpha sine beta, and the opposite side is sine alpha sine beta. Notice we formed a right angle triangle with a hypotenuse of 1 and an angle of alpha plus beta, so the opposite side is sine alpha plus beta, which at the same time is this length, sine alpha cosine beta, plus this length, cosine alpha sine beta, and the adjacent side is cosine alpha plus beta, which is this length, cosine alpha cosine beta, minus this length, sine alpha sine beta. So we now know these two identities, that is, the sum angle formulae for sine and cosine. Alright, now let us simplify this expression for the derivative of sine of x using the formula we just derived. Factor out a sine of x, and then we get this expression with two limits we have to find. Let's solve this limit involving sine first using the squeeze theorem. For an arc of the unit circle of angle theta, the sine of theta is less than the arc, theta, which is less than the tangent of theta. Divide every part of this inequality by sine theta and then take the reciprocals, which mind you switches the signs, but you can just rearrange. Now once you take the limit as theta goes to 0, we notice that sine theta over theta is equal to 1. So that solves this limit. Okay, but now how do we solve this limit involving cosine? The usual method is to multiply with cosine plus 1 on both halves of the fraction, and then we'd get cosine squared dx minus 1, where we could use the Pythagorean identity to solve for sine, and then use the limit we solved previously here again. However, that doesn't work in our case, because duh. Let's go back to this and try to solve it in a different way. When we're here, instead, let us maybe use some sort of angle sum identity for both of these. We can write sine of x plus dx half plus dx half minus sine of x plus dx half minus dx half. Notice that dx half plus dx half is dx, and dx half minus dx half is 0, so we're not actually changing anything. However, now we can use the sum and difference angle identities. Let's first find sine of negative x and cosine of negative x because we'll need that. We could derive this algebraically too, but then we'd need to derive another formula. Let's just use the unit circle definition for these functions. So in the unit circle, after a rotation of theta, it forms a triangle of hypotenuse 1, height sine theta, and base cosine theta. If we look at sine of negative theta, we move clockwise, and this half is negative for sine. So sine of negative theta equals negative sine theta. For cosine, moving clockwise doesn't change anything because this right half is positive, this left half is negative, so it doesn't matter whether we move clockwise or counterclockwise, so cosine of negative theta equals cosine of theta. Alright, back to the derivative. We get the following, where these two terms cancel out, leaving us with this term twice, or 2 sine dx half cosine x plus dx half. This is wonderful because now we can write the limit as such, where this limit is the same one as we solved earlier, which is equal to 1, so the result is that the derivative of sine of x is cosine of x. How relieving. We use the same method to find the derivative of cosine of x by writing it as cosine of x plus dx half minus cosine of x plus dx half minus dx half. Then simplifying, we find that the derivative is equal to negative sine of x. Because the derivative is a linear operator, the derivative of negative sine is the negative of the derivative of sine, which we derived, so now we know all the derivatives of sine and cosine. Delightful. Also, let's just quickly find the derivative of e to the x. We factor out e to the x and get this limit, which simplifies to ln e, which is 1. As for the derivation, I'll put it on screen here. So the derivative of e to the x is e to the x. Now we move on to Taylor series. The idea of a Taylor series is that we make a polynomial where each derivative of that polynomial at a point equals the derivative at that point of some function. For example, let's write e to the x as a polynomial. For now, we don't know the coefficients of this polynomial, but we'll figure them out along the way. Let's match the constant term of this polynomial at 0 with e to the x at 0. So all terms go away except for the first one, giving us 1. Then let us match the derivative at x is equal to 0 with the polynomial and e to the x. So take the derivative on both sides, input x is equal to 0, and solve for the unknown variable. Also match the second derivative and the third and the fourth and so on until infinity. Doing this gives us a sum which approaches e to the x as the number of terms approaches infinity. That's right, using an infinite polynomial we can describe e to the x. This is called a Taylor series. A Taylor series is an infinite polynomial whose derivative at a point matches that of the derivative of some function. Here we found the Taylor series of e to the x at the point x is equal to 0, because the nth derivative of this polynomial at x is equal to 0 is the same as the nth derivative of e to the x at x is equal to 0. Specifically, in this case, it's called the Maclaurin series, because a Maclaurin series is a Taylor series situated at x is equal to 0. We can write the Maclaurin series for e to the x using summation notation. Finding the Maclaurin series for sine of x and cosine of x, which I'll leave as an exercise for the viewer, we get this. Note that all of this still hasn't required the Pythagorean theorem. Furthermore, for e to the x, let's replace x with ix, where I is the imaginary unit with the special rule that I squared equals -1. So we get this for e to the ix. Then let's write the real and imaginary part of the sum. The real part is all the terms that don't have an imaginary component, while the imaginary part is everything with an imaginary unit in it. So we can factor it out, thus it can be written as a plus bi. In general, every complex number can be written as a plus bi, where a is called the real component and b the imaginary component. Notice that the real part of the series is the Maclaurin series for cosine of x, while the imaginary part is the Maclaurin series for sine of x. Therefore, e to the ix equals cosine of x plus I sine of x. How interesting. By the way, plugging in x is equal to pi gives the famous result e to the I pi equals -1, or oftentimes written as e to the I pi plus 1 equals 0. This equation is frequently cited as the most beautiful equation of mathematics. Personally, I have strong feelings about this equation, which might sound silly, but it is what it is. Now let's solve for cosine of x and sine of x individually. We take e to the -ix to be equal to cosine of x minus I sine of x. And although we could do this methodically using linear algebra, it really isn't necessary. We can easily figure out that cosine of x equals e to the ix plus e to the -ix over 2, and sine of x equals e to the ix minus e to the -ix all over 2i. Now lastly, let's compute cosine squared x plus sine squared x. After some simple algebra, we find that it's equal to 1, so sine squared x plus cosine squared x equals 1. Using the definition of sine and cosine in relation to a right-angled triangle with angle x, opposite side O, adjacent side A, and hypotenuse h, O squared over h squared plus a squared over h squared equals 1. Multiply with h squared on both sides of the equation, and we find out that for right-angled triangles, the hypotenuse squared is equal to the legs of the triangle squared. Or rewrite the sides as a, b, and c for the hypotenuse, and then we get that a squared plus b squared equals c squared, the Pythagorean theorem. If I somewhere accidentally use the Pythagorean theorem, then do point it out, and if you can come up with a more absurd proof, then do share.